Good morning. Myself, Professor Rajendra Givari from Department of Electrical and Electronics Engineering. Today we'll be looking at Module 2, second chapter, three-phase system. The contents of this chapter are brief introduction on three-phase system, Faraday's law of electromagnetic induction, generation of alternating voltage, advantages of three-phase system over single-phase system, and generation of three-phase system. Brief introduction on three-phase system. There are two types of system. One is single phase and the second one is three-phase system. In single phase circuit, there will be one phase and one neutral, and the single phase voltage is 230 volt, which is usually used by our homes and small premises. Whereas the three-phase system is nothing but a three single phase voltages. In single phase system, we have one phase and one neutral, which is going to generate single phase voltage. But in three-phase system, which is nothing but a three single phase voltages of equal magnitude but displaced by 120 degree. A three-phase system is a pair of generator and a load, in which the generator is going to produce a three sinusoidal voltage, or you can say three single phase voltage of equal amplitude and frequency, but at the same time they are differing in phase by 120 degree from each other. Now what do you mean by generator here? Generator is a machine which converts the input mechanical energy to output electrical energy. A generator can be also called as an alternator. Now alternator is a machine which generates three-phase voltage, AC voltage, right? That is alternating voltage. Now this generator is used in almost all power stations such as hydropower plant, nuclear power plant, thermal power plant, wind power plant. If you take an example of hydropower plant, the source of hydropower plant is a water. And if the water is going to fall from certain height on a turbine, so turbine is your mechanical part or a prime mover, you can say. So mechanical part is your prime mover. So once the turbine rotates by the fall of water from certain height, the turbine is connected to the alternator, and from the alternator we are going to get three-phase voltage. Right. Therefore, three-phase systems are commonly used in generation, transmission and distribution. We generate three-phase power, we transmit the power through the towers, and we also distribute the electrical power from substations which are near to our area. Next, before going to the next slide, first we'll try to understand what is Faraday's law of electromagnetic induction, or what is the principle behind Faraday's law of electromagnetic induction. Basically, all electrical machine such as AC machine or DC machine works on the principle of Faraday's law of electromagnetic induction. It states that whenever a conductor is moved in a magnetic field such that it cut across the lines of flux and an EMF is induced in the conductor. You have a conductor which is moved in a magnetic field. So the magnetic field is nothing but a magnetic flux which is produced by two monopoles. One is north and one is south, which are in opposite direction. North and south are facing to each other. Between these two, there is a constant magnetic field. Now, if you move a conductor in between the magnetic field, this conductor will cuts the lines of flux. Therefore, because of that, an EMF is induced in the conductor. And if the conductor is going to form a closed circuit, it will cause a current to flow in it. If the conductor forms a closed circuit, it will cause a current to flow in it. Therefore, for generation of EMF, there should be a relative motion between the conductor and the magnetic field, keeping any of them as a constant. So looking at the principle of Faraday's law of electromagnetic induction, there should be a relative motion between the conductor and the magnetic field, keeping any of them as a constant. So looking at the statement, we are trying to move the conductor in a magnetic field. So how does the magnetic field is produced? The magnetic field is produced by two monopoles, north and south, which are stationary, and the rotor is rotating. So there is a relative motion between the conductor and the magnetic field, wherein we are keeping the poles, that is north and south pole, constant to generate constant magnetic field. Let's take an example with a picture. Now this is a coil which is connected with a galvanometer, and on the right side we have a north pole and south pole. This is a permanent magnet. This is a coil with a galvanometer. Now in the picture it is showing a deflection, but when the coil and the magnet are stationary, there is no deflection observed in the galvanometer. It will be at 0. Next, when the magnet is moved towards the coil, the needle of the galvanometer is going to deflect in one direction. When the magnet is moved towards the coil, we observe that the needle of the galvanometer deflects in one direction. Now, when the magnet is held stationary at that position, the needle of the galvanometer returns back to 0 position. Now, when the magnet is moved away from the coil, there is some deflection observed in the galvanometer, but in opposite direction. And once again, if you keep the magnet stationary, the needle of the galvanometer returns back to 0. A similar observation can be found by keeping magnet as a stationary now and moving the coil towards the magnet. If the magnet is held stationary and the coil moves, and if the coil moves away and towards the magnet, the galvanometer shows a similar deflection as what we have seen when the magnet is moving towards the coil. So let's take with a tabular column position of the magnet and deflection in galvanometer. If the magnet is at rest, no deflection observed in the galvanometer. If the magnet moves towards the coil, deflection is observed in one direction. If the magnet is held stationary at the same position after moving, if you're keeping the magnet as stationary, so the needle of the galvanometer will come back to 0 position. If the magnet is moved away from the coil, the deflection is observed in the galvanometer, but in opposite direction. But again, if the magnet is kept or held stationary at the same position, that is moving away from the coil, the needle of the galvanometer will come back to 0 position. So this is how we can see how the magnet and the coil are trying to create an EMF in the galvanometer, or the voltage is induced in the galvanometer. So there should be a relative motion between the coil and the magnet to generate an EMF, keeping any of them as a constant. Okay, so this is the principle behind the Faraday's law of electromagnetic induction. In order to understand better, you can go through this link and watch the video. Next. Now, generation of alternating voltage. This we have studied in module 2 first chapter, Right. Now to understand the concept of three-phase power, we must understand the generation of alternating voltage and the shape of the waveform, which is always a sinusoidal for AC. Right. Now in order to understand this, we have two monopoles. Sorry. We have two poles, north and south, and we are trying to keep a conductor in between those two poles. Now consider a conductor of length L, which is placed perpendicular to the lines of flux. So the flux are coming from north to south, right? And if we keep a conductor of length L placed perpendicular to the lines of flux, so from the front view it is just a dot for a conductor, right? So let's try to imagine you are considering a conductor of length L which is placed perpendicular to the lines of flux of constant flux density. So there is a constant flux density coming from these two poles. Let the conductor rotates in circular motion with angular velocity omega. So the conductor is going to rotate in anti-clockwise direction. Right. Now when the conductor is at position 1, its angular displacement is 0. Therefore, the conductor is moving parallel to the lines of flux. Hence, no flux is cut by the conductor and no EMF is induced in the conductor. Therefore, the EMF induced is 0. When the conductor reaches position 2 by making an angle pi by 2, so it is a 90 degree, you can see with the center part. So when the conductor reaches position 2, rotating through an angle pi by 2, then the conductor moves perpendicular to the lines of flux. Hence, the conductor is going to cut maximum flux and maximum EMF is induced in the conductor. So at one position, the EMF induced is 0. But when it reaches position number 2, this conductor is moving perpendicular to the lines of flux. Therefore, it cuts maximum flux and maximum EMF is induced in the conductor. Similarly, when the conductor reaches position number 3, there is no flux, no EMF. So it is 0. Again, once the conductor reaches position number 4, by making an angle of 3 pi by 4, the conductor is going to move perpendicular to the lines of flux and maximum EMF is cut by the conductor, or maximum EMF is induced in the conductor. So and once again, if the conductor reaches position back to 1, from position 4 to position 1, there is no flux, no EMF. So at position 1 and 3, there is no EMF. At position number 3 and 4, we have maximum EMF. So you can see at 2 and at 4 we have maximum EMF, and at 1 and 3 we have no EMF, it is 0. So that is why for alternating voltage we get a sinusoidal waveform. It is just for the explanation, we have taken two poles and one single conductor. Right. Now what are the advantages of a three-phase system? A three-phase system apparatus is more efficient than a single phase apparatus. The power in three-phase system is constant rather than pulsating, and the three-phase motor starts and runs much better than a single-phase motor. The size of the three-phase alternator is small as compared to single-phase alternator. The three-phase motor produces uniform torque, whereas the torque produced by single-phase motor is pulsating. Three-phase motors are self-starting, whereas a single-phase motors are not self-starting. So these are the points which are important for advantages of three-phase system. This question can be asked for 5 marks in the exam. So please go through this. Now, generation of a three-phase voltage. Any electrical apparatus such as generator or a motor. Now, as I said, generator is what? Which converts mechanical energy to electrical energy. Now, what is motor? Motor is a machine which converts electrical energy to electrical energy. Sorry. Motor is a machine which converts electrical energy to mechanical energy. You can take an example of pumping a water from your ground floor to the top tank. You just switch on the button, your motor will start to try to put the water and fill it the upper tank. So it's a electrical to mechanical. So any electrical apparatus such as generator, motor, transformer or rectifier having one winding is called a single phase system. If these above apparatus are having two windings, then the voltage generated by them or the current flowing through them will have a phase difference of 90 degree. But if there are three windings in the machine, then the voltage generated by them or the current flowing through them will have a phase difference of 120 degree. Then they are called as three-phase systems or polyphase system. Electrical apparatus having one winding is called a single phase system. If the electrical apparatus have two windings, it is called as two-phase system. If the electrical apparatus have three windings, then it is called as a three-phase system or a polyphase system, wherein the voltage generated by them or the current flowing through them will have a phase difference of 120 degrees. This is very important point. Now, electrical machine which generates three-phase voltage is called alternator. Any electrical machine which generates three-phase voltage is called alternator, and alternators are also known as synchronous generator. Now, generator is electrical machine which converts mechanical energy to electrical energy by the means of prime mover into an AC or DC, whereas alternator is a machine which converts the mechanical energy to electric energy by the means of prime mover into AC only. Right. So generator is a machine which converts mechanical energy to electrical energy by the means of a prime mover into AC or DC. So in generator we have AC generator, also we have DC generator. Therefore it is saying it can generate AC or DC. But alternator is a machine which converts mechanical energy to electrical energy by a means of prime mover into AC only. Now the alternator consists of stator and a rotor. It consists of two parts, stator and rotor. Stator is stationary, rotor is rotatory. So here we get a picture of electromagnetic induction. So in order to induce an EMF in the conductor, there should be a relative motion between the conductor and the magnetic field, and keeping any of them as a constant. So the alternator consists of two parts. One is stator, which is stationary, and the second one is rotor, which is rotatory part. This is very important. Now here the stator is in cylindrical shape and it has uniform slots in its inner periphery. The conductor which forms the winding of the alternator are placed in these slots. You can see the pink color are the windings which are placed in these slots. These windings are connected together either in star winding or delta winding fashion. We'll see what is star winding and delta winding for the next topic. Now, the rotor. So the stator is what? It is a cylindrical shape and it has uniform slots on its inner periphery. and these slots are carried with windings which are connected either in star or delta. Next part is rotor. So stator is stationary. Rotor which is rotor which is a rotating part of an alternator. Rotor is a rotating part of the alternator which is represented by two poles, north and south, as a sake of explanation for the generation of three-phase voltage, which produces constant magnetic flux density as shown in figure 2. Right. So the stator is stationary, the rotor is rotatory. So here stator is acting as like your coil and your rotor is acting like a magnet, right? Okay, I hope you have understood. So this is your stator and this is your rotor which is placed in the stator. So stator is the outer circle, outer frame, and in that stator, in this stator, you are going to place the pole. So stator is your stationary, rotor is rotating, and stator is acting as a coil, rotor is acting like as a magnet. So what happens is that once the rotor rotates with certain velocity, once the rotor is going to rotate with certain velocity, the conductor or the stator conductors are going to cut the flux produced by the rotor conductor. Therefore, an EMF is induced in these conductors, right? So how does the rotor is going to rotate now? So the rotor is going to rotate by the means of a prime mover. So alternator is a machine which converts mechanical energy to electric energy by the means of a prime mover into AC only. So the rotor is rotated by the means of a prime mover. Prime mover is nothing but your turbine. The turbine can be a hydropower plant turbine, hydro turbine, it can be steam turbine, or it can be wind turbine, it can be thermal power turbine, it can be steam turbine where a steam is heated at a certain temperature and it's been hit on the turbine, right? Now, so once the rotor is rotated by the means of a prime mover, the rotor is going to produce its own flux. Now, how does the flux is produced by the two poles? Now here we are not using a permanent magnet. Here it is a electromagnet. We have a steel cast steel, and on that we have some copper windings, and to that we are supplying DC. Why DC? Because DC is a current which does not vary with time. It remains constant. It remains always constant. So once a DC current is applied to this particular winding, it's going to generate constant flux. A current carrying conductor will produce a magnetic field around it. A current carrying conductor will produce a magnetic field around it. Therefore, when you supply DC to this, it will generate magnetic field by supplying DC to this, DC to the poles. So field is produced. So this rotor will rotate. Once the rotor is going to rotate, the stator conductors are going to cut the flux, and EMF is induced in the stator conductor. So this is a three-phase conductor. Now looking at this picture, here A1, A2, B1, B2, C1, C2 are the three independent coils which are placed electrically displaced by 120 degree. So look at A1 and B1, this is 120. If you look at A2 and B2, it is 120. If you look at C1, B1, it is 120. If you look at C2, B2, it is 120. If you look at C2, A2, it is 120. If you look at C1, A1, it is 120. So three-phase system is nothing but three-phase winding. So they have three windings which are placed electrically, which are displaced by angle of 120 degree with respect to one another in the stator as shown in the figure. So once the rotor, so this is a rotor now, it rotates in the stator with the help of a turbine. The flux produced by them sweep across the stator conductors, and hence an EMF is induced in the three-phase. So whatever EMF is induced in the three-phase will have again a phase displacement of 120 degree with respect to one another. I hope this is understood, because this is very important topic. This can be asked for 6 marks. Now this is how the waveform of a voltage generated are sinusoidal. So it will have 3 windings. So we are going to get 3 single phase voltages. So this is your first voltage, which is having E is equal to Em sin omega t. This is my second winding voltage, which is Eb is equal to Em sin omega t minus 120 degree. This is my third voltage, which is Ec is equal to Em sin omega t minus 240 or Em sin omega t plus 120. So this waveform is very important. So try to practice this, and you have to draw this for the exam. Now, how does the 3 windings are vectorly represented? So when we say that the three coils which are placed in the stator are electrically displaced by 120 degree with respect to each other. So this is how the conductors are placed by this angle. So this is my first coil, or the first winding, which is EA. This is EB. This is EC. So from EA to EB it is 120. From EB to EC it is 120. From EC to EA it is 120. So the these three coils are independent, and they are electrically displaced by 120 degree. Once the EMF is also induced in the 3 windings, again they have a phase displacement of 120 degree with respect to one another, right? So the equations of the voltage induced in 3 windings are: EA is Em sin omega t, EB is Em sin omega t minus 120, omega t minus 240. It can be written as plus 120. So EB lags EA by 120 degree, EC lags EB by 120 degree. From the waveform, it can be proved that the sum of the 3 EMF at any instant is 0. That is, EA plus EB plus EC is equal to 0. Now write all these equations. So EM is constant here. So sin omega t plus sin of omega t minus 120 plus sin of omega t plus 120. So after calculating these, you are going to get the sum of the 3 EMF at any instant is 0. So just try to calculate this. So here they have used sin A minus P, sin A plus P. So if you use that formula, you can get the answer as 0, 100%. Right? So this is very important question. You cannot miss. Please go through this generation of 3-phase voltage. What is the electrical machine? What are the parts of it? What exactly it converts? This is also important. How we're going to place the coils. There are 3 windings: A1, A2, B1, B2, C1, C2, which are electrically displaced by 120 degree with respect to one another. This is your stator, and they have slots on its inner periphery, and this is a rotor, which is rotatory part, and it is going to rotate with the help of a prime mover, and this is going to create a magnetic field. How? Saying that there will be some windings on this particular pole, and to this you are supplying DC, so that you are going to generate constant flux. DC is going to give you constant magnetic flux density. That's why we are not applying AC. Okay. Hope you have understood the class. If you have any doubt, you can ask me, or you can message me. Thank you.